Hi everybody, hopefully you can see the opening slide of my presentation there. So my name is Michelle Spruce. I'm a PhD student at the University of Exeter in the UK. Very much interested in assessing the social impacts of extreme weather. However, today I'm going to talk to you about a study which we're getting ready for publication regarding using social sensing of high impact weather and see if it's useful in impact verification. So the problem essentially is that we've got an increase in impact-based forecasts, which give advice and warnings about the potential impacts of weather. And then we also have those impacts of weather. But some of the challenges of evaluating how well we forecasted those impacts is that at the moment, a lot of the traditional meteorological observations don't give us information about how people were affected by the weather. Damage to property, disruption to daily life, information about where flooding happens. All of that information is harder to get hold of. There's been some existing work to try and establish information on impacts, but it's reasonably labour intensive and has its limitations. So this is where we come in. Could social sensing help with this impact data collection? But what is social sensing? So essentially, it's the analysis of unsolicited social media data. That means, it's just out there. There's been no filter on it. And can we use that to detect real world events of interest? And there's been a number of studies which have used social sensing to have a look at and detect natural hazards and find information about impacts from those hazards. Most studies use social media data from Twitter, mainly most social media platforms. There's privacy issues and you just can't easily access the data. So, and also Twitter's very much available. It's very real time in terms of its user population. Many existing studies also, they tend to focus on one particular event or one particular location. Okay, so having a look at previous work, so we've been working with Joanne Robbins at the Met Office, and she has in the past looked at evaluating their global hazard map. I'm not going to go into too much detail on this because this is very much Jo's area, but essentially the global hazard map is a summary of where high impact weather is going to be forecast across the globe for the next 7 days. And so what Jo's team are interested in is how well is the GHM performing in terms of did the forecast weather result in a high impact event? And they've developed some impact-based evaluation methods to evaluate how well the GHM has been working. So this study published in 2018. Essentially, there was a manually created impacts database where information on impacts for different high events was collected from a number of online news sources and social sources. And it was pretty good. A number of events were detected. There was good accuracy in terms of when the event was and where the event was, and there was quite a lot of impact detail. But putting this together is pretty labour intensive, and there's also an increased likelihood that events are going to get missed from this database, purely and simply because it's just so the resource requirement to put this together. But what this database also has is, because we've got detailed impact information, it can categorise those impacts in terms of severity. So we have severity classifications from low impact all the way up to disaster, where there's widespread or pretty bad damage. So that's categories 1 to 4. So that kind of sets the context of previous work. So this study that I'm talking to you about today is really to explore the potential of social sensing to help as an impact event detector. And in this, we filter and locate Twitter data to find heavy rainfall events. One of the issues that we have with social sensing is the lack of ground truth to verify things. So what we've done in this study is we've used the database, which was put together by the Met Office, as a benchmark for us to compare our Twitter data to. We extracted tweets from across the world, containing keywords relating to rainfall itself or the impacts of rainfall, floods, landslides. And we collected data for a 6-month period from January to June in 2017. Okay, so this is just to show you the kind of volume of Twitter data that we've collected. So over the 6-month period, 44.7 million tweets, which contained one of the keywords that we'd been searching for. But the problem is there's a lot of irrelevant data in there. So we need to filter that data to only get those tweets that are actually relevant to a high impact rainfall event. And after we've applied some filtering, we're left with about 5 million tweets. So quite a substantial data set for us to work with. In terms of the methods for doing our filtering, we remove automated bots and weather stations. There's a lot of automated weather stations out there which are constantly sending tweets. Neither of those things are actually going to tell us about the impacts of weather. We also remove irrelevant terms. So often some of these weather words like flood and landslide, they're used in other phrases. So floods of tears, won by landslide. So we want to remove tweets that contain those phrases. And we also apply machine learning through a naive-Bayes algorithm. We built a training corpus of a few thousand tweets, which we read. We tagged those tweets. Is it relevant to a high impact event? Is it not? And then use that as a training corpus to run through all our remaining tweets and say, is it relevant? Isn't it relevant? And we had pretty good success with that filter. Another issue that we have with our tweet data is we don't necessarily know where that tweet came from. A very small percentage of tweets actually have the exact coordinates of where it came from. So we also need to apply a location inference process to infer where that tweet came from. And we use the user's location in their profile and or the place name that's mentioned in the tweet text. So a combination of those gives us pretty good indication of where that tweet came from. So that's how we kind of get to our data. So once we've got all our tweet data, we've aggregated it together into areas across the world. We've aggregated it using the GADM administrative areas just down to level 1. So that's like the first level of a subdivision within a country. So that's US states, or within the UK, that would be England, Scotland, Wales, for example. And as you can see from this plot, we got pretty good global coverage. We've got tweets from across the globe. What you can also see there by the black points are where the events were recorded in the Met Office database as well. So the next thing to do then is to kind of look at, where are we seeing peaks in tweet activity and where was weather actually happening. So the first thing we did was, rather than using the absolute number of tweets, we did a proxy for that, so kind of normalised to account for population in a place or just propensity for using Twitter in a specific location. So rather than using the absolute number of tweets, we calculate the percentile of the tweet activity on that day compared to normal. So what you can see here in this plot is by the dark blue spots is where there's unusually high activity talking about rainfall. And when we compare this with the rainfall radar for the same day, you can see by eye, there's pretty good correlation there between the peaks in Twitter activity and where the heaviest rainfall was. What we also did was we looked across the timeline, across the 6 months, and plotted some time series of the number of tweets and overlaid that with where the events were recorded in the Met Office database. So this is an example for Australia. We've got 4 areas in Australia here where there was an event recorded in the Met Office database in that 6-month window. The line graph there is showing you the volume of tweets, and then each of the vertical lines coming down is where there was an event in the Met Office database. And we can see peaks in the tweet activity do correspond quite nicely with where there was an event in the Met Office database. But what's also interesting is there are a number of peaks in Twitter activity which don't correspond with an event in the Met Office database. But when we've drilled down and had a look at that date and gone over old news reports, actually that's a potential missed event. That was an event that caused impacts, which would have meant it met the criteria to be included in the Met Office database. So all very encouraging stuff. So we've eyeballed the data, but the next thing we need to do is apply some sort of metrics to the data so that we can more accurately measure how well it's performing. So we count the number of matches between the two databases, so that's the true positives, and also the mismatches, the false positives and the false negatives. And we calculate 3 metrics. The first one is recall, which gives us an idea of how many events were detected, how good an event detector is our Twitter data. Precision, how accurately are we detecting events? How often does it go off? Does it tell us there's an event when there isn't an event, and vice versa? And then we combine the recall and precision together into an overall F2 score. And we want to favour recall in that calculation. I won't go into the detail on those, but that's essentially what those metrics mean. By plotting those against each other, a number of things we can find out. So in this plot, for each of these points on the plot is using a different percentile threshold in our peaks in Twitter data to calculate precision, recall, and the F2 score. So we start at the 65th percentile and go all the way up to the 99th percentile. The idea being that we need at some point to know how big a peak in Twitter data do we need to tell us that an event happened. So that's essentially what we're trying to understand here. And you can see that recall at the lower percentiles is pretty good, but precision is pretty low. And then as we increase our threshold of tweet percentile, precision improves, but recall decreases. So the threshold we need to use is somewhere around the middle. What we also found was by extending the time range that we looked at, a 3-day window around the point where it rains and where impacts are being reported seems about right. We get the best performance. So we're looking out to 3 days after the rainfall actually occurs. We also did the same comparison looking at English-speaking countries, because we've collected tweets containing English terms, and other language-speaking countries. And while we see much better performance for native English-speaking countries, we also see some quite good performance for other language-speaking countries, which is encouraging and means in future work, we probably need to start collecting terms in other languages as well, which will really improve the scope of this work. We also look at performance by impact severity. The most severe impacts, which is our red line at the top, we detect the most events, which is great. But what's interesting here is the next best performer is actually our lower impact events. But the reasons for this are most likely down to the difference in the style of reporting between an individual on Twitter and an aggregated news report. So somebody on Twitter is more likely to report quite kind of low, disruption to their daily life as opposed to aggregated together. We also looked at factors which affect performance. Different locations in the world see differing levels of performance. The reason why there's a lot of white on here is we just looked at areas where there was an event in the Met Office database. And also, this is the final plot, we also looked at the number of tweets in a place and compared it with the F2 score, which is our measure of how well social sensing is working. And what's interesting is actually the number of tweets in a place doesn't seem to affect how well social sensing works, which is great news for sparsely populated areas or places in the world where people are less likely to tweet. So in summary, our main findings were that there's definite potential for social sensing to be used to help collect impact data. We saw good coverage both globally and also in terms of the number of events that we detected. We also detected additional events which weren't in the Met Office database, which is really good. We saw best performance for English-speaking countries, but as I said, we can improve the performance for other language-speaking countries, perhaps by adding in terms in other languages. And volume of tweets doesn't appear to be a factor in performance, which again is really great. In terms of future work, we'll look at considering some sort of real-time application so that we can detect events much faster than waiting for news reports to come out. And also, once we've collected all this Twitter data, those tweets contain text, which is telling us information about how people were impacted, not just where they were impacted. So that could help with getting information about the impacts they experienced and also the severity categorisation. So that's everything from me. Thank you. So any questions?
Thank you, Michelle, for your talk. So now would be the time to either put in your questions in the comments section or just raise your hand. You can unmute yourself. Let's see. Okay, we have a first question. So Martin, would you like to unmute yourself? Or should I read it out? If I don't hear anything soon, I'll read it out. Okay, so we have a question from Martin, and he would like to know if in non-English speaking countries, you still looked for English terms, right? So, okay, yeah, so the applicability to other languages, so.
Yes, so we only collected tweets containing English terms. Yes, absolutely. So in other language speaking countries, that obviously limited the data that we would have got from there, but we still did get data containing those English terms from those places.
So while other questions will probably pop in, I would be really interested. So it's impressive work that you've done. I think most services use the manual extraction method that you also, which is very tedious indeed, right? So yeah. In terms of automatization, can you recommend any easy tools for the beginner? I mean, there's a lot of commercial tools, but can you elaborate on that a bit?
Okay. The Twitter Developer API is reasonably accessible. So one of the issues is you have to collect the tweets in real time. So you can't go back more than about 7 days in terms of getting the Twitter data without spending a lot of money directly with Twitter to buy the tweets. So you need to set up some sort of collection in real time, and you can either set it up based on a location by putting in a bounding box or by searching for keywords. And there are various Python packages out there which will help you to do that. So Twython being the best one.
Okay, perfect. Thank you.
Thanks.
So we have another question in. So from Brian Mills, I'll just read it out. Does your social media search time frame include anything impacts associated with bonding once some expectation of an event has been circulated, e.g. traveling, shopping ahead of a storm?
That's a really interesting question and one that we've discussed. In this case, no, we didn't look at before the event. The idea being that we were more interested in the impacts as a result of the weather rather than as a result of the weather warning, if that makes sense. So we're kind of interested in, you know, where the flooding is, where landslides occur, and those kinds of impacts. But yeah, it's interesting. In other studies, we have looked at prior to the event and seen how the discussion on Twitter changes in terms of what people are talking about before the event, during the event and after the event. So that's still an interesting area to look at, but we've just not included it in this particular study.
Okay, one more thing from my side, if you would allow the question.
Yeah.
So there's been, what you mentioned in the end, also look at real-time extraction. So I think low latency information retrieval from social media is a big topic, right? So have you had any experiences there yet? Maybe preliminary?
Yes, so we already within our research group developed a tool to look at floods in real time in the UK. People talking about floods on Twitter in real time in the UK, and in terms of a time lag, that all works pretty well. So yeah, actually, it's certainly doable. Obviously, it's going to be slower at times where you've got high volume, but because you are kind of applying these filters and what have you, then it does work pretty well.
Okay, thank you. We have another question. Actually, I didn't see that there was a raised hand, so sorry for that. So, Professor Sieber.
Hi. I gave my talk last night. Unfortunately, it's not compatible with Europe time. I'm really on. So we do both supervised and unsupervised classification of tweets. I was curious whether you knew of the work of Imran and Crisis NLP in how your method compares with his.
So I am aware of that paper, and thank you for sharing it. In terms of how our work compares with his, I probably can't give you a very detailed answer today on that one. Yeah, it's a different way of looking at it to the way that we're doing it, I think. Because I think that was more of a manual process in terms of annotating the tweets and then applying the machine learning approaches, I believe, if I've understood it correctly from my memory of that paper.
Well, they have, you're right that it is very difficult to do the annotation. They have 16,000 annotated tweets, because you mentioned impact, and they have a fair number of impact categories, and that was a very painful process. They did create a process to automatically label another, I think, 6 or 9 million tweets. So it might be good to go back and see how your model compares, because your model might actually have some improvements over their approach.
Yeah, absolutely. Yeah, I think we've sort of used what works, and yeah, you're absolutely right. It'd be good to go back and look at that study. Yeah.
And also, you may want to look at BERT. There are modeling approaches that I think are somewhat better than the standard supervised classifications. I have a paper out about the use of BERT for supervised classification. So, I mean, this is deep in the weeds for everybody else, but there are many different types of modeling approaches for both supervised and unsupervised classification, which makes it extremely difficult for people who are not data scientists to do this.
Yes, yeah, absolutely. Yeah, and then perhaps you and I could have a discussion afterwards. I'd be really interested to kind of look at this a bit more. Yeah.
So that seems like a very good idea. So thank you for the input and the questions. There's also a reference in the comments by Professor Siebert. She put a reference there, so you might want to check that out. But I think we can really discuss this later on. We will have lots of time. Next up, so thanks again, Michelle.